Hello, good morning, everyone. We are going to get started. It's time. I was waiting since I saw people joining half a minute or so for everyone to come on board. But I think it is time to start. You might have noticed that I was trying to get to share screen, but then I may kind of lost the place where I have my chat session, and I wanted to follow along there. And so for a second, I have stopped, but I will come back to sharing. This time, it's not going to be slides. Otherwise, I set everything up so that it is more like a machine. I just run it in a way when we get started. But today we'll go a little bit back and forth. So welcome to class. This is the first of a new month, April 1st. And I'm going to start with a warm-up question relating to the date itself. I know in some of our cultures in the West, this is April the Fool Day. So I'm not going to tell you anything that's appropriate for an April the Fool. This will be a class as it always is. But I'm a little bit curious if April 1st, April the Fool is a culture that is known wherever you are coming from. So if that's the case, you say April 1st, the Fool is a known quantity in our culture, in my culture. If it is not, and if you've got something that looks like that for another month, another day of the year, I am very curious to know. So the warm-up question of the day is April 1st known in your culture? If not, do you have something similar in your culture, and would you mind sharing that? That's the warm-up question. I'm sure I did a terrible job formulating it, but you know what I meant to get to. So go ahead and participate. That's the reason I wanted my chat session to be available, so I can see what you will be saying there. If you observe, if you celebrate April the Fool, go ahead, tell me. If not, if there is anything else in your culture that resembles like that, you do that too. What I want to do today is spend some time talk about the project ideas I have kept telling you I have for potential semester projects for this class. Before I do that, the reason I'm doing that is not necessarily because not all of you have project ideas. You have, and you are very strongly encouraged to keep thinking about it, keep to propose it. But you may not. And sometimes, even if you have, if you see some other ideas, you may want to see if there is any way to incorporate and things like that. And this was in my agenda. This was in my mind for a long time. And I didn't put that document until today, essentially. And so the document that I will go through and what I will explain is uploaded on Canvas. And I have a module that says semester project, and many of the things that are related to semester project were being added there, right? So we have had things around the team formation, what project is. I had several documents uploaded already there, so it is added, and so you will find it there. And I will talk about these ideas to varying degrees today. And the other reason what I want to talk about them is because some of them are actually related to topics we discuss anyway. So whether you take up a topic for a project or not, like for example, graph clustering was a topic in this class, similarity was a topic in this class, like many other things. So there are very fundamental topics that we would need anyway, which is what we did the first 6 or so weeks. And then there will be a little bit of, a topic that might fit to a project, but you will not personally take it as a project, but it is still important. So the topics that I would be talking about today, along with these ideas, are of that nature. Some of them are upcoming topics that we'll look at a little bit in more detail. And so that is another reason why I want to spend some time now. So the last lecture we had was on graph similarity, and I told you there will be a follow-up lecture to it that will look at similarity between graphs. And we will need at least one good lecture for that. And the upcoming time, next week on Tuesday, is what I have decided to do that. So if we have enough time after the discussion today and so on, then I may start talking about that. But if not, then that will be the time reserved for talking about graph similarity, an extremely important topic in many ways, especially with things related to mining, graph mining as it is called. So that's the reason. But let me also, before I get to kind of discuss what I want to do today, start by clarifying things. I wanted you to submit your project proposals on Canvas, and I told you, starting from this point on, anything that is related with project will be teamwork, including the submissions. So you will work as a team. and you will submit project proposal, project itself, and the presentations. This will be as a team. Some of you, most of you are a team of two, some of you are a team of three, and there is one exception, one or team of one. So whatever the size of your team is, there will be one submission. So to be able to do that, on Canvas, I wanted to create an assignment that's group, which I did. And I followed everything that Canvas told me to do. And it asked me how many groups there will be, and I did 13. But then I never got to a place. I was looking for a chance to actually determine which group, how the groups are formed, who is a member of each, and I didn't get that. And I did find out ways to do that, but I have not completely done that yet. What I did instead, after I know, or after some of you notified me that you did get notification from Canvas where it told you that you belong somewhere, which was not what you intended to do. You probably got confused. So forget that. Ignore the message that you got from Canvas, but there must have come a subsequent one, I believe, because I did choose another option that said a student can decide, or whatever, the student can choose the team they belong to. And I just created the teams empty, from my angle at least, 13 of them. And what you would probably be prompted to do would be to say you add your name in the team that is. And so for convenience, we can just go by the team numbers we said we will do for when I set up the updated team members, right? The 13 one. That document, you've got numbers there. So that was arbitrary. Let's just use that and stick with that. And so go sign up there. So let me first, now that I have asked you about April the Fool and whether you celebrate it or not, let me come back there and see now if the second notification, the one that I explained now, you got that on Canvas. Did anybody get a notification about signing up for a group? Okay. Okay. So what you do then is you go sign up, and you will, I think both of them, everyone should sign up for their teams. Remember which number you belong to, and you sign up there. And Canvas will assign the first person that would sign up for the team will be group leader. And to me, what it means is if there is ever a need, I would communicate with the team as a team, but if there is ever, for example, if there is to submit, I don't want multiple copies, so a single copy is enough. So that group leader could serve the person who submits it. That's a good way to describe a function for what a group leader would be. And so Canvas will assign you to be a group leader, and that assignment will be just the person who signed up for that group first. So I'm glad that it has worked out, because I was going to try an alternative means for creating group. Yes?
My audio cut out. What are we signing up for on Canvas? I did not hear that part.
Yeah, so the semester projects are team-based, right?
Mm-hmm.
And to submit, for example, the first thing that you will submit is a proposal. So the team will submit a project proposal, right? So that will be a document. And this document, like everything else that you have been submitting on Canvas so far, is called an assignment. That's how I would grade it. That's how I would you get a chance to submit, and I get a chance to view it. These things that are related with the project now will also need submissions. And for this one, I needed to create an assignment, which means a way to submit them, and they will be group-based. And so that's what the group is. It's just, I am saying these teams now correspond to groups on Canvas, and that's what you're signing up for. It's not a new thing. It's just,
okay.
Yeah, it's a little bit of a roundabout way for me to even explain it, but I think it should be clear now. Is that clear, Vincent?
Yes.
Yeah. So you're not signing up for anything new. You're just, yes, that is, Riley, you're right. This is what I was going to do now. I haven't. I read up on this, and this is how I would have created the groups myself. But it looks like I may still need to do that. I will, but that's the procedure. What I was doing, if you speak Canvas now that you are giving tips, Riley, is I was looking at this from assignment. When you create an assignment, you create an assignment and you follow certain things. I was trying to create this group assignment via that, which was not successful in getting me the people I want to be in a group. But what you have described, Canvas to go to people and then create groups is how a group is formed, regardless of whether there is an assignment or not. All right. Is there anybody who is a TA and uses Canvas? Or you don't have to be a TA, you may be instructing a course. Okay, what course are you TA for? Okay, okay. So you know you're working with Shakira, so I know she uses Canvas. So if okay, now I know at least there is someone I can go ask if there is anything. I think Canvas has been working. I am impressed. I like it very much. It's easy to use and very organized. And I hope your experience with it has been good as a student also. Some of your classes are still on Blackboard. Starting from next semester, everything will be on Canvas. Yes, it is true. All right. Okay, so I think we are now all set. I'm going to tell my idea. Okay, I think now I can start sharing screen. Okay, is this clear enough for everybody? Can you at least see the font size? This is the place where I'm losing my chat session. I don't know where it's going away from me. And it kind of feels a bit awkward not to be able to see that piece.
What do you struggle with not being able to see, Professor?
What I'm struggling to find is the chat window.
Okay. So in your screen share bar, there should be a like 3 dots that say more.
Yes.
Click that.
I did, and I found chat, but I don't know which screen on one of my 3 screens this chat window is showing up.
That's that I can't help you.
Yeah, I know, and this I used to not have this problem because I set up everything before the class starts. I can't locate it; it's just absent. I think I can live without this. So I'm going to ask you to do me a favor. So if you have something to say, any one of you, please unmute yourself and do until I find out where my chat session has decided to show up. So I don't have like too many options. I've got 3 screens, and it's not in any one of these as far as I can see. Oh, okay. All right, now I can find it. All right. So we're good. Okay. So I'm going to, so I guess the answer was yes, that you are able to see this. We will do this informally and take it partly as suggestions for project ideas and partly as at least appetizers for some upcoming topics and for some of them to see where they are used. And so don't tune out even if you know which project you're going to be working on. Let me begin by asking you what your status is. I know today is April 1st, and I have set the deadline for submitting your project proposals for Monday. That's April 5th. If I'm giving you these ideas and I want you to think about them and potentially select one, it is close. I know that. So I don't mind extending by a couple of days. What I would like to happen is for you to have enough time to do a good project that will satisfy you, that you learn a good amount from, and a good project in the sense that you get good evaluation and get good grades at the end. Both of these are important. And for those of you who do a good job, I still would like to work for very few ones. If you do really a good job, I'll be happy to collaborate afterwards and see if things can be turned into a paper. So you have a very many good reasons for having to spend enough time and do a good project. And so the project proposal, to get it approved and to submit early is a good thing, because then you'll have more time. So if I push it, then it will be more time for you to get approved and move on. So let me first hear if the 5th is good for everyone. I remember some of you have asked for a couple more extensions, days of extensions. That extension would mean borrowing 2 days into your project, implement whatever it is, like time you would spend working on it. So let me see if the 5th is okay, or if you need it to be moved to the 7th or something like that. So some of you start saying something on the chat session, and that would be okay. 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 I need a couple more. Okay. Okay, I think this is enough of a response. So I think what I will end up doing is give you up to the 7th. And if you finish and you are ready to submit on the 5th, you can always do that. And if I have the time to actually look at it, I can get back to you and say, go ahead. What you should expect from me when you write your project proposal is primarily, if there is any major comment I have, whether it is adequate to be a project, or if it is something that needs addition of some change or something like that. So approval or not disapproval. It's not graded for quality because you have not done the project yet. The project, when it is done, is going to be very carefully evaluated through your final report and the class presentations and whatever addendum I would ask you to put in the final report. So no worries about having to score highest point or anything like that. In the past, what I have done is at this stage, if a project proposal is accepted, approved to go ahead, then you get 100, in a way, full credit. There isn't anything in between. But what you want to do instead is to make sure that you hit the 5 or 6 bullet points that I have mentioned that a project proposal is supposed to accomplish, makes them that do that, and do a legwork for yourself, because now you have thought about it carefully means that doing the project will be easier for you. So unlike these assignments or whatever things that are graded, where there's right and wrong, there is quality assessment, there isn't. What is assessed is whether it is going to be approved or not. So I will make it 7th, and I'll go back to Canvas to change the submission date, extend the submission deadline. If you are finished, submit. If not, use it until the 7th. So we've got 48 hours extension. Okay. Let me then tell you this project ideas. And I think this is fairly large enough, and you can follow along if you download the PDF that I have. I'm showing now the Word version. It's actually many. So we've got 13 projects, and if 4 or 5 of these get selected by some of you is fine. But I wanted to describe them all, and I have grouped them into areas, 5 areas. And there are, if you count every single project idea, then there will be 12 of them. And the way I have described them here is to make them self-contained. And if there is a reference or something that accompanies what that project is based on, or if there are some good readings associated with it, they are mentioned in the place where the project idea is described. At least the area is described. And some of the ideas would be collective references. So unlike other documents where I would have all the references at the end, this was got references at the end of each section. And I'm going to also tell you the area is not ordered in anything particular here. It's not, maybe a little bit of difficulty, I guess, is there, but not so much. So some of the easier ones may be in the middle, and they may be sandwiched between things that are harder and things that are not that hard. All of them are substantial. And this would probably also give you an idea for what your own idea that you are entertaining to come and suggest now when you submit, where they would fall. What you will see me describe now has something that we have never done in this class so far. There is no topic so far where we mention the word machine learning, because that's not what this course is about primarily. But it is also not a big surprise for you that almost any area these days will have something to do with machine learning. Don't be cynical about that. It's actually a good thing. And one of the reasons most of these things happen is because we've got lots of data. And network science is not an exception. In fact, you might have also kind of picked up this, and maybe it might have struck you, because the way we think of social networks, information networks, or other networks, biological networks, when we think of them in terms of network science, we are emphasizing the interactions, the relationships between entities. And we could think about things that are related with structure, as I keep telling you, and dynamics as processes that happen on the network. But we should not forget that the nodes, or sometimes the links, also are rich in data. And now you can imagine what you could do if you've got both of them. Because whenever there is data, you could, try to get some insight out of it, knowledge out of it, model it, and learn things and things like that. What if you had both of these? Because what is absent in traditional type of data, multidimensional data, is just that data richness, sometimes very high dimensional and complex, but there is no notion of relationship that's binary, which can be modeled as a network. But plenty of things have both of them. And for this reason, it has become more and more common. In fact, many of the conferences I go to these days do have their bulk of work at the intersection of these. And these things go both ways. Things that would be helped because you look at your data in terms of networks. By the way, that's one of the places where this thing that I told you about signed networks, were co-spectral clustering. I don't think I included it here. I forgot to include it here. Idea is rich. It's very important. And it is when you look at things that are similar with positive edges and dissimilar with negative edges and look at them simultaneously to co-cluster, that is one area, one example where the direction would go one way. The other direction is when you have network, and what you want to do now is kind of get away from the kind of approach we have had in this class so far. Think of it as a graph, think of it as a network, come up with an algorithm, solve something on it. In addition to do that, is there anything I would gain if I turn this around and make it and much like what other data problems are, and then use machine learning and data mining techniques on it to solve a graph problem? I am not necessarily a big fan of that direction because sometimes it's abused and it's done incorrectly in the sense that the whole thing about what the graph was kind of gets lost, but sometimes it is the right thing to do. And so the first thing I have here, one of the project ideas, deals with that. When is it good to embed a network, to turn it into some other dimension so that you can do some work with it? And there is a very large body of work, literature around this, but I'm going to both talk about this and at the same time motivate kind of problems where something like this would make sense. And I call this network embedding. And embedding here is used just like you would encounter embedding in many other places. Graphs are nice, networks are nice. You've got two things to worry about: nodes, edges. I've got the nodes, mostly you can even think of them as discrete quantities, and I've got the edges. It is a relationship, binary relationship between these. That's all there is. But what if you were to turn this into, embed them in another space so that you could do more things with them? But these things that you would work with are going to be obtained from the network that you started off with. And that's essentially what the idea is in network embeddings. And these things are important when you want to study from a little bit of temporal aspect. So for example, how a network has evolved over time, how it has changed over time. Biologists do this. And Eric may agree, sociologists may also have a reason to see how a network evolves over time. How did it grow? You've got some kinship, some relationship between groups of people, and then it changes over time. And if you closely follow them, and if you study what they're doing, you may have explanations. But would the network itself tell you how it evolves? This is where triadic closures would come in. This is where homophily and things like that would come in. But what if these networks are not like biological or social, but they are technological or information? And then you may see change, and that change may be a good indicator. A good indicator, for example, if there was a fraud, if this interaction that the network was representing was about banks, then the way this thing has changed over time may show you something that drastically changed, and there may be a suspect. Or if it was communication network and there was some bad packet that went wrong and things like that. So change over time in a network, to closely monitor it and to know how it has changed, is important for these things. So the two examples I gave you now around security and fraud detection are graph mining problems, and they will be empowered if they were going to be using other data mining and machine learning techniques. So we may need to embed them. So what I wrote here and what I said do not necessarily kind of one map, but I have kind of complemented or supplemented what is written there, so you have more things to think about. So there are different approaches for having to do network embedding, and these are all good. Some of them have a little bit of attractive nature, others would have a little bit of specialized applications when they would come. I will group them into, I think, 2 or 3 I have. One of them is based on factorization. To do network embedding. And this factorization, I'm thinking now linear algebra. So when you factorize a matrix into, you know, if I had a matrix A and I'm factorizing it in L and U, or if I have a matrix A and I'm having a singular value decomposition of it, SVD, or even principal components analysis. That type of factorization is what I'm thinking about. And now, what is new, that's not new, having to look at the adjacency metrics of a network and to look at how it could be factorized is to reduce dimension. Basically, you are embedding it. Is not new, but what this project idea has is to think of this problem when things vary over time. And so you could do like this is a matrix now, and I am thinking about how you may decompose this into 2 like SVD without the S in here. And so it is matrix factorization, but one of them is fixed, the structure of the matrix or the certainty aspect of the matrix, and there is something that's temporal. That's what this subtease try to show you. So to try to do this in a manner that respects time is a big challenge. And this is probably one of the most challenging problems I could imagine among the ideas given here. I'm not discouraging anybody from jumping on it, but it is challenging, I should say. The word challenge here is used to mean a different one. You'll see me say challenge everywhere. What I meant is, what is this about? What is the thing to do, the problem? When I meant challenging was about this particular project idea was the level of difficulty. So I've got a little bit of an explanation for this. If you are sufficiently interested, you can take a look at it and try to attempt it. And this is not meant to give you you know, like a prescription on how to go about it. You're open to, there's a few suggestions for what the goals of this project might be and what you could do, but you can come up with your own ideas for having to do it. Factorization-based network embedding, essentially having to look at how a matrix can be decomposed into 2 when the matrix has to do with the network, where one of the pieces is time dependent. So it's a little mathy, a little heavy on what pieces you would need, but real cool project. I've got a few additional references for this that are fairly recent ones. I know some of you are computer scientists, some of you are not. Computer scientists, when they say, that includes me, recent, they mean like now we are in 2021, 2020 is recent, 2019 is recent. Anything past that, oh, it's very old. It's disappointing sometimes because I actually don't think there's so many new things happen in a year or 2, but that's the kind of recency. What I meant here is what I would have said this to my other colleagues in other areas where things happen slightly, you know, more slowly. And so 2017 result is really recent. But I think generally speaking, this, I would even consider them recent enough for you to do. I am sure there might have been some follow-up works by these people or anybody who kind of took on their work. There may be more recent ones than this, but I think this is a good place to start to read about them. That's one way to do network embedding. Another, for time barring one. Another thing to do network embedding when your problem of interest is to study dynamic or change over time with networks is to think about what everybody these days does almost, is to use deep learning, neural networks. And so there are neural network-based time varying network embedding methods. I would not recommend this if you have not taken either one of my class, my data science class or a machine learning class or a dedicated deep learning class. So ignore if you don't have anything, if you don't know anything about neural nets. If you do, then consider this. And I don't think it will be appropriate for me to spend too much time rather than pointing out its existence here and its importance in a way, if you happen to be one of those people interested in this. And I've got a couple references for it. This time, I think I could fairly say I think there might have been some more work after this, but these are among the good ones that came around. I think I will come back to this point where I have indicated here as semi-supervised. This is the context in which the work has come. I will come back to it later on, but this is an important topic that has got good use for graph algorithms. Tony's presentation on graph clustering, where label propagation was discussed, his DOLPA work, he's mentioned at that time, and Alex and several of you understood why it was called semi-supervised, when label propagation is used for the purpose of machine learning. That is when you are classifying basically, and you've got labels, but they're in limited supply. And so you've got only some of them, the others are not there. And so you want to propagate the ones that are known in a manner that would be most effective. That is the genesis for the label propagation algorithm in machine learning. We used it, Tony's works, very successfully for doing graph clustering because it has got its appeals, right? But the idea, the essential idea was used for supervised learning. In that case, it was called semi because you don't have all the labels. These embedding techniques that I told you now that are neural net based came around because of semi-supervised classification. I'm going to come back to this theme in one of my later ideas. That was the second way in which you can think about network embedding could happen: factorization based, neural net based. The third one is random walk based. And I'm not trying to be exhaustive here. These are the project ideas and how they are classified. It doesn't necessarily mean this is only 3 things you can do or 3 avenues for doing networking, but that's not what I mean, but it's a good selection. Random walk based ones are very popular and very successful in many cases. And the random walk that you see there is a random walk you encountered when we talked about PageRank. We looked at PageRank and we studied it fairly carefully. And I told you, and I hope you have appreciated why it's so important an algorithm. We had these 2 ways to derive it. One was the random surfer model, and the other one was what Kleinberg called it, the 2-step or the 2-fix iteration or something like that. And they arrived at the same conclusion, how the PageRank algorithm would behave. But the random surfer model was helpful. And you can now go along the same lines about having to do random walks in a graph to do network embedding. And that itself is an interesting problem, but it is even more interesting when the graph is temporal. It's changing over time, and you wanted to find good ways for doing that. So this project idea goes around that type of thing, and it's got a little bit of an explanation, a little bit of concrete things that you could do with this project. And just like the other 2, 3, I've got examples of works that are related here. I think I could say at the time I compiled these were not only for recency, but these were the most impactful works and then the best work. Node to Vec, I'll come back to this one. I'll talk about this when I talk about graph similarity, is one of the most popular ones. And it has been successful for having to do things of all kinds of variations. So the first people who introduced this did it to find an embedding of nodes into vectors, basically. But then the idea for it comes from natural language processing, and it is used in many, many areas now. So I think now that I'm telling you this, I hope you're following me along. I am not introducing project ideas to you. It's also a good survey in some ways. And so I think regardless of whether you pick them or not, some of them you would definitely want to look up and read up a little bit more on. That would be probably sufficient walk. We had a random walk, but it's not all that random around network embeddings to talk about. I'll relate network embeddings to graph similarity in the upcoming lecture now, and you will maybe hear me one more time come back to some of these terms in a more organized fashion when we have slides around them and a little bit of an explanation. But you've got an appetizer for that now. What I have in the remainder of this section of this document is data sets that would make sense when you are working with networks that vary over time, and the evolution of them is of interest. And one way you may come up with your own way to think about when something like this would be of interest is to think about networks where the edges have timestamps. So for example, if it was a phone call, and so now you've got, this is when it has happened, or if it was a bank transaction, then, entity A with entity B, they had this transaction, money transfer, and the edge is stamped with time. And many other things like that. So these networks that you see here have got that nature. I really want to encourage you to think about places where you may think timestamps may be available. There is a whole lot of things that you can do. People like Joe may know this in economics and things like that. If you have or logs, something has happened on the web or things like that, and you've got a log, and one of the pieces of information you have there is time. And you could do a lot of things if you take advantage of that piece of information. How did it change over time? If there was time, how did it change over time? What went up, what went down? Can you then do predictions and things like that? So these data sets have got that peculiar, or not peculiar, but that nature of their edges or their links having timestamps on them. All right, that was project area 1. I've got 5 to go, and I should maybe pick up some speed here. The second area is what I call core periphery. Let me see if you have any questions so far. Any questions on project area 1? Anybody who's tempted to take any one of those? I have located my chat window, so I know what is going on. So. Okay, so silence here means there is nobody who's thinking about picking any one of those. That's what it means, right? Okay. And again, silence means yes. That's great. Okay, let me go to the second one. This is a structural issue. There is no time here, but it is a very important one. The topic of clustering or community detection would make us think that networks have some kind of organization that lends itself to community structures, and we discover them. And it is true. There could also be another way networks could naturally organize themselves around. And this is termed as core periphery structure. And what it really means is, if you look closely, the nodes in a network may have, when you have, let's say you have visualized them, there may be a portion of the network that is at the core, in which you could think of it as relatively well connected with one another, but it is more at the core in the sense that it has captured the majority of it, and physically it would have been a core if you were to visualize it in a two-dimensional space. And then there will be some nodes that will be like on the periphery. They will be attached to only one or two, which are not so much attached to the rest of the network. Networks do have that structure also. And these two are high-level organizations of networks that are relatively perpendicular to each other. So the modular structure in which networks have communities and this organization may be present at the same time. It's just there is two different ways to look at them. Unfortunately, not so many times is the core periphery structure of a network studied. But when it is studied, it has made very good impact, because the discovery of that structure could be helpful. And so I have project ideas here that are not as well developed in the sense that there is much text, but I've got some rough ideas about them. But I was intrigued by this a couple of years ago, and there was one project that a student did that we found very interesting things. And I wanted to expand upon them a little bit and tell you about a couple things that are here. Whoever is interested in this work could be interested either from a theoretical perspective and look at what this one is, because as I told you, it's not studied very much as it should, as much as what community structure of networks is, but there is a lot of room. But the ones that are available, the algorithmic understanding of it and the models and maybe the algebraic interpretations of it is a good one. But if somebody is interested in taking that a step further, that would be one great idea. So the point is, networks are organized in a manner where you can find a core periphery structure to them, where much of the network is around the center, where most of them are connected to one another, and there will be some that are only peripherentially attached to the rest of the network. This would make sense also in social networks, because you've got some people who are not really into it, right? They're there, but they're not really into it. And so they would just maybe have got a couple friends who are not all that connected to the rest of it either. And so they would be called peripheries, whereas the other ones are going along really. And so they have, it doesn't necessarily mean they're a clique. It doesn't necessarily mean like the communities, you've got, multiple pieces. This is more like a two piece. So you've got this core and you've got this periphery, and you could dial this up and down a little bit and then say how much of a core it is. And so if you loosen that definition a little bit, then you could say, I will call only this portion a core, like 70%, and anything out of that score and the value that you may associate, you may call it a periphery. So it is a diable. It is something that you could tune, and it's a very nice framework, very much complementary or orthogonal to how you would investigate community structures in a network. That was the theory part. And the application part is, if you were to look for data sets where something like this is suspected to exist, and you look for them, and there are some good codes, a couple at least, that could be used to find these core structures, core periphery structures, then what would you then discover? And this one, I've got a couple ideas. One is in the context of, I think it is going to come. So the readings I have for this project ideas for the theoretical ones and so on, like the other project area, are described first. So I've listed them here. So let me skip that and take you to the place where there is application for if you were to discover this. One is, I think it is probably by now all done, but people who were studying toxicology, something that is about toxic substances that cause cancer, among the many network science methods that they could use, the one that helped really find very important discoveries, and I know some of you have interest in knowing about cancers for certain things. They may not be the kind of cancers studied here. That was an essential tool to find out that relationship and discover structure. Another place where core periphery structure was used for a good thing was predicting economic aspects between countries and within a country between industries, where I don't think it is that hard to imagine there will be a portion of the network that's like more of the core. This is where the big thing is happening. And then there will be some that have just peripheral attachment to the rest of them, or on the periphery. And that was found to be a good predictor. And Bitcoin is another area. So I'm not saying so much about this, but I think I gave you a little bit of a clue for why they may be relevant for a core periphery structure type of study. What I have done in addition to mentioning the ideas here is try to help you, again, if there is anybody interested in one of these projects, is try to help you how much work there is, how much new work there is in terms of implementation, in my judgment, at least at the time I compiled this, and how much of a potential it has for having big impact, for example, to be turned into a paper. So that's what you see, these weird things that I have called original coding required, data cleaning required, and publication potential and things like that. So take it as a little bit of a gauge on my part to try to give an indication for why this might be. That is as much as I wanted to talk about project idea too. Okay, does core periphery sound interesting to anybody? Or does it resemble some of your thinkings in your own project ideas that you have? Okay, so again, I would interpret silence to mean no. Let me also admit, if you're hearing for the first time what I'm telling you now, I don't necessarily expect you to have an opinion right away. So it's okay if you think about it after we finish this to see what you may get out of it. Let me come back now to semi-supervised learning, and this is project area 3. And this is where semi-supervised learning is taken as the main topic. That's why I have grouped it here. And what it is needed here is it's also in some cases related to what's called active learning, is to deal with the fact that labels are expensive. So anything that you've done, so for those of you who've done something around machine learning and classification problems, you sometimes have a problem and you've got different ways to formulate it. And the more natural way to formulate it would have been as a classification problem if only you had labels, right, for the training data, if you had enough labels for them. But you may not. Or if you were to insist that you would do a supervised learning problem and you wanted to get labels, you may, but it may cost you. It may cost you to label data if you were to hire some people, or if you were to meticulously do something else in another way, but all you are doing is to label them. If you were to turn an image and try to, for example, having something that has to do with image processing type of machine learning problem, and you needed to train your data for medical applications, and you wanted to see how doctors have decided about x-rays in the past or something like that. So there may be something that is expensive or sometimes inaccessible for having a complete set or a complete training set with labeled data. In that sense, you may want to go with limited labeled information, and that's why semi-supervised learning would come in. This is where active learning comes. I don't talk about it a whole lot here. Then you may have this other problem to say, which ones then should you pick, for example, to insist that you should get a label? And what else can you do when you can take advantage of the limited labels you have? In those situations, graph-based approaches are useful. And one of the places where graph-based information would be useful is to use graph signals. This has to do a little bit with things around signal processing, Fourier transform, and things like that. They are called graph signals, and I have got a little bit of a description. This may appeal, I don't know, to people like Gabe, I guess, or somebody who had a little bit of interest in something that is more at, or whoever has done with anything that has to do with things that you could call signal processing type, something that has to do with waves or sounds or lights and things like that, where you might have encountered this in a more natural way. Graph there are important, and this is the kind of thing that this talks about. And I've got a few suggestions for how to define a project around this and use data mining type of ideas to do enables semi-supervised learning. I've got a few references that you could look at to see if this is of interest. And all of these ones are good ones, even if they are not the latest works. All three of them are good references on this topic. Project area 4 is my lab's work, and I want to spend a little bit of time telling you about this one because there may be something that you could do new, and you've got more access to things that are finished compared to the first project areas I described. The first project areas I described, some of them have got codes, but then they are not ours, and so they may work, and they do work, but we don't necessarily have a lot of handle over them. This project area is work in my lab, so we have codes and things like that that you will have better control over, and you can do more interesting things. So let me try to, and I don't think there would be any chance in the course where we will have a topic like this coming up. So it's not a bad place to tell you a little bit about them. And let me watch out my time. I think I have enough time to tell you about this. So the story, or this is biology. Biology is the primary driver here, but it doesn't have to be related to only biology things. In fact, there might be several of you who may have interest of on topics that are about strings anyway, text processing, for example, or databases, if like you are RIAL and you're taking a data, or you're TAing for a database class. So not all data is multidimensional in the sense that you've got numbers around them and you've got these different dimensions, you've got height, weight, and it's not necessarily like that. Sometimes there just may be sequences of, strings. And you want to do something with them. So biology is full of them because you've got proteins and DNAs and things like that that are about sequences, and you want to manipulate them. So one common question that may come then is, let's say you've got a database of some kind and you've got sequences. Don't worry too much about where the sequences are coming from. They are sequences and they've got certain lengths, and you want to typically want to do something with them, sequence analysis. You may want to align them and see how much of a common thing that they have and whether they differ and things like that. And they take you to some degree somewhere, but not necessarily very far. What you could do even more is if you were to think about these sequences and generate a network out of them by looking at how similar they are. And these things are called sequence similarity networks. And so every node in this sequence similarity networks is a sequence, and it will be connected with another sequence if it is sufficiently similar. And so to talk about when are they similar, you'll have to compute distance between them. And there are different things that you could do to compute distances between sequences, and many of them are expensive to compute, and that's an issue. So let's say, for a second, I will delay that discussion about how expensive they are, but let's say you've computed and you've decided when to put and when not to put, and now you've got a network. Now this network could be analyzed for all kinds of things, and sometimes it reveals something that is not possible if you were not able to look at them as networks. So the work we did, it's called DI1, and the DI there is directed, and it is weighted. That's where the W is coming from, and the rest of it is ANN, and that's all nearest neighbors. So what people do usually for the sequence similarity network I roughly described now is to take their database, compare networks with one another, compute their distances between them, all of those pairs, and then decide with a certain cutoff to say if the distance between these two sequences is greater than this, then they're not similar. They're far apart, so they will not be an edge. But if it is below this cutoff value, then they are similar enough, and we'll put an edge. And that is what traditionally the work around this area is done. They could vary in how they do the computations and so on, what cutoff value they would use, but this will be what they do. And so you've got a network that you could then cluster and do whatever network problem might be of interest. But the problem with having to do that is you will have to decide empirically, you'll have to know the area good enough to put where your cutoff will be. And sometimes there is no good rule. And sometimes people would kind of reduce the cutoff until the place they would get a network after all. Otherwise, it will be either very sparse, or it will be just completely dense and it will become meaningless. And so that manipulation of having to do cutoff and knowing the empirically determining it is a challenge, in addition to having to compute all of the pairwise distances between pairs. What we came up with is a smarter idea where you would worry about, when you build your network, only to the thing that would be closest to you. And that's what the NN is, nearest neighbors. This is common in machine learning. If you know about k nearest neighbors algorithm, for example, you look at the in some Euclidean space, the closest ones, the k closest ones to you, and then you label yourself like them, right? That's how k nearest neighbors classification would work. It's similar in that sense, because now you're a network, a sequence, and you compute your distance from others, and you would care about the one that's only the closest to you. When they are further apart, you will not care to put an edge. So there's no thing about cutoff here. There's no thing about weight to put a cutoff to build your network. Instead, you always would look for, if you are a sequence, look for the one that is the closest to you, regardless how far apart they are. They may be very close to you in terms of actual distance. sequence distance, edit distance, or they may be further, but at least you would keep to the ones that are closest to you. Because these are sequences and the distance between them is edit distance, it's very likely that you would have ties. So a sequence would be equally distant from multiple other ones. And so if they are the closest, we keep them all. That's what the all is in our model. So this is in a nutshell what DAI1 does. So for each sequence, it will look for the sequences that's the closest to it and keeps them all when they are tied. And to show that this is how far away they were, the actual weight is incorporated in the network. And so now imagine you have a network computed in this fashion. It will always be connected, which is a big advantage. And we did get some very good biological results because of that. The graph, there's no cutoff. The disadvantage is there are edges that you never even considered to put in, you never even bothered to put in your network because they were things that were a little further away than what is the closest, and you've lost information in that sense, but you have kept the skeleton of the network, and that was extremely helpful for us. That's what DAI1 is. And the project ideas I have, this is work done already. We've got an algorithm efficient one and some very good tool to build it. But the distance calculation, even though we prune things that we don't need to compute because they are not the closest, still has got some room for improvement, or somebody could come up with some other ways to measure distance than edit distance. Edit distance is what is currently used, and that is by nature very expensive to compute. And so one of the project idea revolves around having to come up with alternative ways to measure distance for a DAI1 network like that. And the other idea is to use the DAI1 construction. We used it for biology, for sequences, and there is a little bit of a description for what we exactly used them. But they don't have to be sequences that are biological nature. They could have been other things. They could have been tweets. They could have been texts that you can get. And now you are, the tweet was probably not a very good example because I don't know if tweets, kind of word similarity will tell you very much. They may not. But there could be other things that are better represented with sequences that are not very long, or texts that are not very long, but they are informative enough for you to worry about. When they are close, they tell you something similar. When they're not telling you something similar. If you cannot come up with something like that, then this model would work in a very good way. And we're using it for some things that are not, they're still sequences, but newer sequences right now in my lab, in fact. But this is the second area, or the second idea around this project area, talks about another place where you could use DAI1. I think I have one more before I let you go. We'll talk about graph similarity next lecture. This one is probably the most difficult in some ways, but also very relevant. How do I say it? So we are interested in this course we have talked about theory of random graphs and things like that, or random graph that we needed to talk about, their limitations. But we also have keep telling you that there are models that are used to synthetically generate networks. The ones you did with your homework 1 and homework 2, the random graph model, but also the Barabashi model is one. There's the small world model, and there is a number of other synthetic ones that have a little bit of stochastic nature to them, a little bit of probabilistic nature to them, but they are synthetic. But they've got a predictive, some behavior that you could write down as a formula even to say how they are constructed, because preferential attachment is the driving thing behind it, or having to, if it was a small world, having to rewire some connections and so on is what is needed there. That is how synthetic networks are generated. And there is good amount of work, including in iGraph and many other places. But there is also another way you could think about generating synthetic networks. And this is closer to what Joe and Katie, for example, will be doing. Suppose there was something about hospital transfers and you wanted to construct a network that represents the patient transfer from hospital to hospital, or one care unit to another care unit. These are real. These networks were built out of things that have happened. And these are things that are not synthetic, they are real world. But what if you were to generate now networks that are synthetic but they are going to resemble whatever these hospital transfer networks would look like, or some other thing. Maybe student transfer to universities, or maybe whatever it is that you are doing in your project and something that you would want to see. How could something that I have access to now as a network that I got and downloaded from Michigan or Snap or one of the places, the website I tell you, they were all real, and there is a lot of advantage for them working with them. But what if you wanted to mimic that? What if you wanted to generate synthetically a network of that nature that is a little bit of data driven? This is what this project area describes, and you've got multiple constraints because of those things. And there are some good ideas described here that resemble machine learning, including GANs. GANs could be used for synthetically generating networks, or they could be something that try to capture what the essential properties of a network are. It's in degree distribution, out degree distribution, clustering coefficient, and so on. If you knew this is what the real world network was, then can I generate another network by having to mimic or try to satisfy these parameters? That's where these constraints are coming from. And so I have a little bit of a description around that, including some the initial ideas for doing it, and some that is, or one idea that is described in a little bit of a detail, and another one very briefly, and then maybe a third one that is even harder. I'm not sure if I would necessarily encourage people to even consider this one. This might be very hard, but the first two are probably accessible to some of you. That was the last project idea I had. Okay, I know what I have done. What I have done is not just tell you about these project ideas. Every now and then, whenever I get a chance, and especially for the topics that I know, we may not get to dedicate a full lecture. I try to use this opportunity to explain them. So it was not a walkthrough of project ideas for you to either take or leave, but also to cover topics that are relevant for our course. That was what I wanted to achieve, but I'm not sure if you if that came across that way.
I had a question on the last idea.
Sure.
So is the last idea also on the lines of what I read while writing my reaction paper was something about sampling of real world networks. So you have a huge network, and if you have to create or mimic a small one, so they use the term sampling of the network.
Yes, so it is related, and that's actually a good point that you brought up. I don't think I have ever used that word, but sampling is an important word here that could be relevant even for dealing with big data problems, as they're called, right? So if you have a network and you have to solve some problem on it, a recommendation problem, for example, and the network is very big, and you will not be able to solve your problem successfully on that one, or it could be something else. It may not be a recommendation problem. Then what would be a good sample of that network that is manageable, that you can solve, that would give you a representative solution for the original? The graph sampling, or ways to generate a network of a smaller size that has got the same characteristics as the original big size, is common for scalability issues, for studying like this. That same idea could be used for generating, which is where you are seeing the connection now. So sampling is an important technique, downsampling, and there is some careful statistical things one can do that is aided by the structures of the network. And some good papers around that too. So that was a good question.
Okay, so is this topic still in scope for the project? I mean, it's in our syllabus, or
yes,
we can go that way?
Yes, it is completely inside. Yes, you should not feel. I think some of you would. I'm eager. I'm going to be looking forward to reading your project proposals, but I am eager to see how much of a connection you would see. So if some of these project ideas that I have described here touch on topics that we have not covered in a main way in the class itself, like machine learning topics. The graph embedding topics I will come back to when I talk about graph similarity next lecture. And I will talk a little bit more than what I did now, but it is not a big topic. the other topics were big. So you should not shy away from having to do a project that is not treated in fact, that is a way to complement the class. Otherwise, you will be doing what the class lectures covered relatively in detail in your project also. That may not be the best way to use your time. Any other questions? Anybody has any other questions? Okay, is there anyone who has maybe thought of either picking up one of these or changing their project ideas a little bit based on what you've heard today? So you're sticking with your original ideas. Right, collaborative filtering has nearest neighbor algorithm idea. Okay, I think, well, so so collaborative filtering is used for recommendation system. That's fine to a project to do. The nearest neighbor algorithm that I'm describing here is a specific kind that is best seen when you consider all of your nearest neighbors and keep them, and the network aspect of it is the more important point. So there is a relationship that you will probably benefit if you read about how DIY works, but it is for sequences and it is not for recommendation. But your project, doing a project on recommendation systems is fine. One thing I will watch out when you send me your when you submit your project proposals is you may have some interesting idea, but if I know that this is something that is likely not something that is novel or your own in a way, that there exists some work somewhere that I know or others would know, then I would discourage that. So recommendation system is a great topic. Collaborative filtering is a great topic for recommendation systems, that is, because there are other ways you can do. But make sure that you do your own project. Yeah, I understand. That is probably the bigger weight I would put in. And I have known, so Canvas would help, but I also know the literature well, and my own students and past works and things like that. I would know when a project is not genuinely yours, generally speaking, but I could sometimes misjudge. Okay. All right. We've got a couple minutes. I don't mind staying around if there is any question that would come to mind.
Since we're off the main class topic, I've got for our group's project idea, I'm percolating around exactly how to represent a data set as a graph. And I'm going to, for the sake of not having to explain as much, I'm going to use an analogy of what the data represents instead of actually saying it. Mm-hmm. Basically, consider like, let's say adversarial sales data. Like you've got a large group of people who are telephone scamming each other, for lack of a better way to put it.
Okay.
If you were going to treat this as a set of weighted directional edges where the weight would be the amount of money and then the direction would be what? Would it represent, would the direction go from the person who scammed the other person, or would it go from the person who got scammed to the scammer? That's the question I'm still trying to play with, and what would either of those represent in terms of looking at the data?
Right. So representing your network or your data as a network is a non-trivial question sometimes, and that could be the place. I have mentioned this several times, where it would make a big difference what you would end up getting. If you model things the right way, by the right, I mean in a way that would best answer a good question, then you go very far. And for example, for this is fraud detection, this sort of thing, cybersecurity and other.
I mean, it isn't actually. It's something else. I'm just saying it's a good analogy for what it is.
Yeah. So what I meant is, like, these things show up and people
Okay.
have considered them as graph problems. But what I wanted to say next was there isn't really anything that would tell you this is the right way, because you may have an advantage, and you may want to think about it a little bit closely to see how you would want to do. For example, there is, once you settle for a directed graph, that is a question yourself you have to answer too, because there will be limited things that you can do when it is directed. When it is undirected, you have got more access to other things that you could do as a network.
I mean, you can easily do it. The thing I was noticing when we were doing like centrality stuff is it's easy to go from a directed graph to an undirected graph, but you can't really make a directed graph out of an undirected one. For a lot of centrality metrics, they're designed around it being directed rather than undirected, which means you get less useful information in that regard. The thing I was noticing when I was doing my reaction papers was that the majority of studies on showing social relationships are always bidirectional, because social relationships are considered, symbiotic, but the data set I have represents adversarial social interactions where one person is doing something negative to someone else. So I'm trying to think of the best way to represent that adversarial nature and be able to gain useful information from it.
Yeah, so direction seems to be the right thing for you to do, and keep thinking in terms of directed work in the network. So what I would then say is, there's no way for ahead of time for you to know which direction
I guess the easy answer, the two easy answers that come to mind is, one, I could create two edges on the graph, one with a negative value and one with a positive value, or alternatively, I could just make two effectively, quote unquote, inverted graphs and just have both of them and then play with both and see which comes up with that more interesting or useful data. Because if I'm running the full code to create one of them, it would be basically trivial to just make the inverse at the same time.
Right. So, but these two things are separate though. So whether a relationship is positive or negative, adversarial or friendly, is separate from which way it is going, whether somebody is the source and the target. So I think the way I understood you first was you have a general idea of having to define the graph to begin with to mean one way or another. For example, the relationship is adversarial, but what you struggled with was to say which way should it go if somebody was spamming. And I would probably follow the direction that would be more intuitive. So if it is spam, then I would make the person who's sending the spam the source, and the person who's receiving the target. In that way, you would have a more natural way to interpret things later on, because in degree then would be being a victim, and whatever it is that this spammer is doing would be more like how many places it has reached, and it will be an out degree. So I think the way the problem that you are wanting to address would probably indicate which direction is going to be the right way.
One kind of counter argument that comes to mind, and why I've been going back and forth on this, is if I'm trying to show which scammer has successfully hubs and authorities, if I had it going, for lack of a better way, if I had the directionality representing the quote unquote flow of money, I could show where it all ends up going, I guess, theoretically. Because again, this isn't like a real thing of people like scammers, but it's hard to describe otherwise. And that might also be an interesting thing. So realistically, making both might be the better option, and then different metrics might show more realistic things depending on which representation you're looking at.
That is true, but there is also one thing what you argued for, having to reverse the direction makes perfect sense. I take that. But when you have competing ideas, and especially when they're almost like opposite to one another, which direction should the edge go? The better thing is not to try both of them and see which one works, because that will always be something that would be the right thing in a way, because now you have tried them, but that's not always feasible in what we do in life, right? So a better thing would be to sit through, to not necessarily have a rigorous analysis of it, but to convince yourself that this will take you to before you implement, that is. And that is usually the approach I take when I teach about algorithms, right? Before you implement them, can you analyze your algorithms that it is going to do the right thing? And then, of course, you go and implement them. Now, this will be what I would say will be better. But your argument about having to do the changes minimal in the implementation is compelling. So you really didn't have too much to do to try out the other one, because it will be minor. Yeah. In that sense, then it probably is even better, because now you have for free tried out the other idea.
Yeah, because it's it's literally as simple as just defining the edge as the source and the destination is reversed, and then you're done.
And I would probably put this as part of your project proposal to see actually to try out and figure out which one is a better one for this modeling. But that's not going to be. I know you to do more, but this will be 10% of it, and that will be nice, in fact, on its own.
Okay. The one other interesting detail that kind of comes up is that there's always going to be one victim, but there can be multiple attackers, for lack of a better way to put it, in a single adversarial incident.
Mm-hmm.
But the data I have does give me an exact representation of how much of a role each of the attackers played in the overall value of the incident.
So you could potentially have a graph that's larger than what you currently are thinking, because you could have links to victim and source
there's also like condensing I might end up doing, so I don't have a lot of parallel edges. There's maybe on a time scale, like on a day-to-day basis, treated as one edge where that can aggregate it out. There's a lot of options on this. I'm not exactly sure the best way to do it right now.
This sounds like very empirical, and I think interesting to try out, because the definition of the graph itself is not given, and there is work there, and this is not unusual. It is common, and your ingenuity may be to actually find out what it is that is the best way to represent this. And the way to demonstrate that is to show, because I modeled it this way, here is what I have been able to accomplish.
Yeah.
That's the only way you can,
Okay. But I mean, now that I've kind of given some analogies of it, I can I'll just say what it is now that it probably makes sense. It's a player versus player killing in a video game, basically, in a large multiplayer video game is basically what this is trying to represent, and then showing the adversarial relationships of this group of players then found this player and killed them. Well, they all had a role in, doing that, but then some of those players get killed by different players, and showing that adversarial social network rather than just a symmetric one of like friends or whatever is why I think this is a lot more interesting than those.
Yeah. Okay. I like this. It's cool. I am going to talk about roles, because you mentioned roles now. This is a social network analysis notion that has got a little bit of relationship with similarity of networks. So I don't think this will change your project in any direction, but I think you would find that discussion interesting, and I'm going to at least mention it on Tuesday or in connection with Tuesday's class. There is actually some very interesting works that happen around this role discovery, as it is called, and it sounds like it has got some connection with what you're saying now.
Because what the existing literature I could find looking at data from MMOs, which the preface on all of this, which kind of confirms something I had already thought, is these video games that have hundreds of thousands of players and exact logging of all the interactions means they make for a lot more empirical data sets than you'd think with social interaction would normally provide, which is why they're good for this. But like most social networks, they're all symbiotic, that they just have this friendly relationship. Or in the case of one of them, they had like, did two players have negative standing or positive standing between each other, but they always treated it as just they had three graphs. One that was a positive graph, one that was a negative graph, and then one was just have they interacted graph, which didn't show a directionality, which is something I wish they'd done when I was looking at the research. And I'm like, I could do that. And then I'm trying to figure out exactly how you represent that directionality, especially since each incident has a distinct value, which the other thing that comes to mind is like that a single player is not going to interact with that many other players, especially if we're doing like a time scale of days, but players are in large groups, and maybe I just treat the group as one quote unquote player, so to speak, and then treat all negative and positive interactions that group did on a given day. That would actually probably create a more like connected network, and that might be a better way to look at it.
Yeah, I think you have many interesting options to consider.
Yeah, sorry, I'm rambling at this point. I was just
it's okay, but I have to let the others go. And
I apologize. Sorry. Thank you for the advice you gave.
No, it's perfect. But I think you can all look forward to what I will be saying about graph similarity in Tuesday's lecture.
Tuesday. Thank you. Sorry.
Yeah, and I have extended. We have agreed to have the project proposal deadline to 7th. I will make it on Canvas. I'll have to stop here, and I will see you all on Tuesday. Okay, take care.